Thank you very much, Marcus, for the presentation, and many thanks to the organizers for the opportunity of presenting here today, and many thanks to all of you for attending this seminar. So yeah, this is basically Hardy's uncertainty principle for metaplectic operators, and it's a joint collaboration between myself, Professor Elena Cordero, that is sitting there, and Eugenia Malinikova from Stanford. The one you read here is basically a simplified version of the original statement, actually a multivariate version given by Sitaram Sundari and Tangavelu in 1995, of the original version of the classical Hardy's uncertainty principle provided by Gottfried Hardy in 1933. It is stated for finite energy signals, function signal 2 here. And, well, it's like any other uncertainty principles, and I thank Irina for the introduction. It is basically stating that a function and its Fourier transform cannot be both simultaneously sharply localized in the corresponding domains. Now, what makes an uncertainty principle differ from the other is basically the notion of localization involved, which in this case is the rate of decay measured by means of Gaussians, parametrized Gaussians. Here the parameters are A and B. The larger the parameters, the faster the decay. And if I read the conditions 1 and 2, I can see that if f decays as a Gaussian and the Fourier transform also decays as a Gaussian, and these parameters are jointly too large, namely if the product of A and B is greater than 1, then f must be 0. Now, a few comments about this statement that nowadays are completely solved. It's just for the sake of the storyline. So first of all, the conditions, the decay conditions are isotropic. Well, this is not a great issue for the Fourier transform for a reason that will be clear at the end of the topic because a huge part of this presentation is really about a sort of directionality feature that is featured by metaplectic operators. The Fourier transform does not feature this directionality for a reason that will be clear. And so here we have isotropic decay, clearly, radial Gaussians. And the joint decay is encoded by the product of A and B. Well, somehow this theorem opened more questions than it solved. So for instance, let's now focus on the condition A times B. It can be easy, okay, it's a weird because you have now in dimension D, 2 domains, d-dimensional domains. And the condition that is merging the directional information of the decay is only 1, A times B greater than 1. We expect somehow, well, let me go. So we can rephrase these conditions in this form. So you basically see the exponents of the Gaussians as inner product in RD, given by these positive definite matrices. If I take the product of these two matrices, now I have a D times B matrix, and we can interpret basically this A times B as a directional information along D directions, roughly speaking, because actually we are pairing 2D directions, so we get D conditions. And to be precise, by the original statement of Hardy's uncertainty principle, we cannot distinguish whether it is necessary for all the eigenvalues. So now A times B are the eigenvalues of this matrix, which are all equal, of course. So we cannot distinguish which of these two sentences is correct. If all the eigenvalues of this product are greater than 1, then f must be 0. Or if there exists an eigenvalue of the product which is greater than 1, then f must be 0. Stated differently, do we really need the decay along every direction for f to be 0? Well, now what we want to do is basically answer this question from the metaplectic for the metaplectic operators. And we will see that for metaplectic operators, it is even clearer that it is enough to have decay along certain directions in the 2 domains. And these directions are somehow related. The reason why you can't see this relation from the Fourier transform is that the matrix of the Fourier transform is the canonical matrix of the standard symplectic form, sorry, the matrix J in Irina-Stock, which has a certain submatrix equal to the identity. And therefore, the directions in the two domains, function f and Fourier transform, are paired, let me say, accordingly. So x1 is paired with psi1, so the coordinates in better. 2 with psi2, and so on. With metaplectic operators, this is not longer true. So I will not introduce metaplectic operators from an algebraic perspective. Just for this presentation, it is enough to interpret them as composition of these elementary operators or elementary unitary operators, the Fourier transform, with the appropriate rescaling so that these operators fall in the metaplectic group. But essentially, up to phase factors, these two phase factors, you have the Fourier transform, chirp products. So basically, you take a function and you overlap very fast oscillations. And finally, rescalings. Take any number of these operators, compose them in any order, and you get a metaplectic operator simply by multiplying by phase factor. The thing that makes these operators so handy is that there exists a projection onto the symplectic group, which basically maps the three operators here to the generators of the symplectic group, namely the matrix J, here denoted by JD, so it's the matrix of the standard symplectic form on R2D, these lower triangular matrices, and the block diagonal matrices here, where C is symmetric and M is invertible. Now, this projection is not, is a homomorphism, but is not one-to-one, because if you multiply each of these generator by a sign, you still get the same projection. But again, we put moduli everywhere, so for the purpose of this presentation, we may pretend that this projection is one-to-one. Therefore, we can interpret properties of metaplectic operators just by looking at the structure of the corresponding projection. The meaningful analytic properties do not depend by a constant. This is what I mean. Okay, so really, a huge part of my work is really trying to understand metaplectic operators from the perspective of symplectic matrices. And in this case, we try to retrace the validity of Hardy's uncertainty principle for metaplectic operators to the structure of the corresponding symplectic matrix. Which metaplectic operators do satisfy Hardy's uncertainty principle? Question. Answer in terms of the projection. So just to see why you can basically, example of metaplectic operators where you basically, where the examples are provided in terms of the corresponding projection. So now you take a metaplectic operator with the corresponding symplectic projection. Just take, the definition of the symplectic group, you saw it in Irina-Stock, but for the purpose of this presentation, you can see that the symplectic group is just the group of matrices obtained by composing this type of matrices in any order. So it's like generated by these matrices. So you can basically represent any symplectic matrix as a 2D times 2D even dimensional square matrix as with the block form A, B, C, and D, where A, B, C, and D are D times D matrices. Now, we can relate metaplectic operators somehow to the structure of this matrix as follows. If capital B is equal to 0, and capital B will be the main character of this talk in terms of symplectic matrices. So if capital B is equal to 0, then it is straightforward to see that the symplectic matrix S factorizes as the product of these two matrices here, with C and M properly chosen. The projection tells us that up to a phase factor, your metaplectic operator with projection S with B equal to 0 is the composition of a linear change of variables, a rescaling, with this product by this chirp. So in the end, we are just rescaling the function f and overlapping these fast oscillations, which clearly preserves the compactness of supports. Now, it is clear that since the compactness of supports is preserved, for these operators, you don't even need to discuss localization properties. They preserve the compactness of supports. So the uncertainty principle of at least the one of Hardy shall not hold for these operators, actually not even Heisenberg's uncertainty principle. Trivial. The opposite case is when the matrix B is invertible, that is, the symplectic matrix S is free, where again you can factorize the matrix S in terms of 4 generators of the symplectic group. And if you take the composition of the corresponding metaplectic operators in the right order, you end up with basically up to a phase factor, rescaled Fourier transform in the end, you see. You have a rescaling for the Fourier transform, and then you multiply by some fast oscillation, which have modulus 1 and usually do not really interfere with the uncertainty principle. Whatever happens in the middle, basically, you can read it by this not as nice as 7 formula, integral representation, where now the integral is taken over the orthogonal complement of the kernel of B, of the blue matrix. And it's not so nice, this is the pseudo-inverse of B, the Murpen-Rose pseudo-inverse, is that not only you are integrating over a subspace over D, but this translation does not preserve the orthogonal complement of the kernel of B in general. So you cannot even change variables inside of F to get, say, another an integral representation holding for every psi, where you are integrating over the same space for every psi. Basically, this is the problem. Okay, this was proven by Termoshke and Onyx in several papers. I mentioned here the one in 2002. And this is actually our starting point for the proof of our uncertainty principle. So let me mention that usually metaplectic operators can be interpreted as follows. You take Fourier transform along a certain directions that now we identify with the orthogonal complement of the kernel of B. And this will be very clear for the statement of Hardy's uncertainty principle. So you take the Fourier transform along certain directions, the identity along other directions, you shuffle the variables a bit with some rescaling, and then you multiply by chirps. That's all. So in the end, metaplectic operators really boil down to Fourier transforms along directional Fourier transforms and composition with some small modification. So it will not be surprising that this directionality will be highlighted in Hardy's uncertainty principle, where we have decays, basically. Actually, many results for metaplectic operators are proven for B invertible because of the nice integral expression, which allows to basically use the properties of the Fourier transform. The other properties are usually known for, there are algebraic properties known because of really the fact that the metaplectic representation has an algebraic definition. So this is a result by Costa Diaz de Gosson and Prata of 2024 for, let me call free metaplectic operators, meaning the metaplectic operators with free symplectic projection, so B invertible, where actually I think one of the most astonishing part of the result is that now the nice isotropic decay of the Fourier transform is replaced with an anisotropic decay, obtained simply by replacing the inner products at the exponents of the Gaussians with inner products defined by a pair of positive definite matrices. And the assertion says, which answers also to one of the questions that I posed at the beginning, if there exists an eigenvalue of this product, which is greater than 1, then F must be 0. So it is enough, basically. So the eigenvalues of this matrix basically encode how the directions in the two domains interact. So we have, namely, D conditions and basically two domains of D-dimensional domains. So 2D directions merged, and the conditions are merged into these D eigenvalues. The directional correspondence between the domains is now encoded by the matrix B, and this is clear now from this statement. It is enough to rephrase this, the second decay direction, decay condition. Look at here. So we have the matrix providing the eigenvalues. B is invertible, so B transpose then B is again positive definite. You can do a simple change of variables and do it again. So now, if S is the Fourier transform, B is the identity. This is the reason why you don't have this interpretation for the Fourier transform. And if you replace the Fourier transform with any metaplectic operator with B invertible, this is how things change. So roughly, this is what happens. So B is is giving you the information of how the metaplectic transformation modifies the directions between the domain of the function and the domain of the metaplectic transform of the function. What happens when B is singular? Of course, you don't have this correspondence anymore. You have it only for a few directions. And in view of the integral expression of metaplectic operators, it is not surprising that the only directions that somehow really affect the uncertainty principle, or actually directionality between the two domains, will be the directions where B is invertible. So this is the statement in the general case. Now B is non-zero because we said that in this case the compactness of supports is preserved. Yes. And but then matrices M and N are now allowed to be positive semi-definite because they only track the decay over along the directions. Let me call them effective directions. I didn't call effective directions these ones in the paper, but basically the directions where B is invertible. Okay. So we only have decay in the domain of F along the orthogonal complement of the kernel of B, and in the domain of the metaplectic transform along the range of B. And the assertion is now the same, but everything is only almost everywhere. Okay? You have decay on the corresponding directions. This is a simplified version of the result. Same assertion. If there exists an eigenvalue of this product which is greater than 1, then F is equal to 0 almost everywhere. And now we see a difference with the basically with the quadratic Fourier transform, with rescaled Fourier transform, which is basically we have a selective decay condition. So we are imposing decay only along certain directions. The joint decay is encoded again by the eigenvalues of this matrix, which you can prove are all non-negative, and there are exactly R eigenvalues which are positive. So you only have in the end to check R conditions to see if F is 0 or not. And only the effective directions are encoded by the matrix capital B. Which one may argue, well, but you are basically asking like a technical assumption for which the theorem holds. Well, no, this is not a technical assumption. Actually, it's pretty necessary, meaning that you can always provide an example of a function with the regularity that you wish. So I took here L2 for simplicity, but which is supported on a cylinder parallel to the orthogonal complement of the kernel of B, whose metaplectic transform is supported on a cylinder that runs parallel to the range of B. So if they exist, the sections along the other directions are always compactly supported, and the only meaningful directions for this uncertainty principle are really the other ones, but they are not mapped one to the other through the matrix B. I'm not stating, I never state the proofs of my results in my talk. The thing that I wanted to stress is that it was necessary to check, and it was not known, that the matrix A maps one-to-one the orthogonal complement, the kernel of B to its image, which is not related in any sense to other blocks of the matrices of the matrix S. So it's, I think it's not possible to write 18 better than this. And also you can put here the orthogonal complement of the kernel of B, everything works. And this was the main core of the proof. Then we had to do some computations and so on. But we started by the formula by Termoshke and on. So, okay, some example. 7 minutes, okay. Now we can prove basically the uncertainty principle by Hardy for the fractional Fourier transforms, where now we allow some of the fractions to be z, basically some of these signs to be 0. So basically, in some direction, you take either the identity or the flip operator. Okay, but this is just a simple consequence of the origin of the theorem that I stated before. So let me just, for the sake of simplicity, state the theorem for the partial Fourier transform with respect to, I say frequency variables because it's the second variable here is in R2, but it's usually, I mean, in the context of metaplectic linear distribution, it is the frequency, so I call it the partial Fourier transform with respect to the frequency variable. I know it's not correct, but so the principle is now as follows. I mean, not surprisingly, if F, this is a more precise statement because now we see that the constants may depend on the points where on the non-effective directions. If f and the partial Fourier transform decay along the second directions almost everywhere, and a times b is greater than 1, then f is 0. So basically, Hardy's uncertainty principle for the partial Fourier transform. Now, so for a more involved applications, our research started by this paper by Helge Knudsen, who proved the Hardy's uncertainty principle for the propagator of a Schrödinger equation with quadratic Hamiltonian, say free particle, uniform magnetic potential, as we shall see, or simply the anisotropic or isotropic harmonic oscillator, under a specific assumption, which we wondered whether it was technical or not, that is, the propagators of this equation are metaplectic operators, and they have their projection. And Knudsen assumed that this block was invertible. And we were wondering, so the corresponding evolution is represented by a quadratic rescaled Fourier transform. This is the synthesis of this result. So this technical assumption, which is B invertible, again, restricts the number of possible Schrödinger equations that we are considering. And we wanted to exclude this technical assumption. And in the end, we did it because we proved the uncertainty principle for every metaplectic operator, and in particular for the propagators of Schrödinger equations with quadratic Hamiltonian. So apologies, this is another more precise version of the result, where now I'm highlighting the directions. And so you see here again that if you take your Schrödinger equation, your propagator is a metaplectic operator, the operator mapping the initial datum to the solution at time t is the propagator. So S hat of t as a projection. If for a certain time capital T, we have that this matrix is not 0, and the initial datum as well as the solution at time capital T have the decay requested for Hardy's uncertainty principle to hold, then you basically formulate your Hardy's uncertainty principle. If you have an eigenvalue of this matrix which is greater than 1, then u must be 0. So the initial datum and therefore the propagation must be 0. Here I'm taking u0 in Schwarz, so the almost everywhere part vanishes, not present. This is the classical example that one usually does. The anisotropic harmonic oscillator. It works also for the isotropic harmonic oscillator, but we wanted to do stuff, more fancy stuff, where the propagator is basically a fractional Fourier transform along the second variable. And therefore, you see here basically that the only direction that counts is the second one, y. Okay? And the uncertainty principle assumes this form where we are taking for simplicity, no, not for simplicity. So this is the condition on the eigenvalues, basically. A times b greater than 1 divided by sine square of t. Of course, because we are assuming t non-zero, otherwise we know that the uncertainty principle simply doesn't hold. But this was pretty, this is a straightforward example. Then the example that usually a few people do is the uniform magnetic potential, which is not in the paper, by the way, but I put it in the presentation, where this is the Hamiltonian, and Q here, capital Q, is an orthogonal matrix, D times D matrix, which has the property of having Q transpose equal to minus Q. If you compute the Hamiltonian flow, the projection of the propagator, now you find this is a symplectic matrix. And using the fact that this block transposed times the block D, this other block, is a multiple of the identity, you can actually basically, in the simpler case where capital M and N are multiples of the identity, just to simplify the computations, you can see basically all the situations where Hardy's uncertainty principle hold. If Bt is 0, then no uncertainty principle. This happens when T is k pi divided by 2 omega. Whenever you have that B of T is, okay, in the other case, these are the cases where you don't have invertibility. In all the other cases, you have that Bt is equal to Q, sorry. The second case is when B is equal to this matrix, corresponding to these times that are the caustics, basically. Then this is the condition for the solution to be 0, and if B of T is invertible, well, okay, the condition is the same. I guess these are a few not update references. I mean, the ones that we put in our paper. And I thank you very much for the kind attention. And